So thank you very much. And over to Robert from Google, who will tell us about the Go language in 3 easy pieces.
Thank you very much. So we've heard a lot about managed and managed languages, native languages, and about the intersection of those and how this is becoming a happy place. And the one thing that I took away from some of the previous talks was that this happy place is getting very, very, very big. So we believe in small and comprehensive and understandable. Welcome to the managed but native world of Go. So what is Go? Go started out as a project between a handful of people that were pretty frustrated with the state-of-the-art in systems programming. We wanted to have an alternative to some of the very mainstream systems programming languages out there. We believe in programming languages that you can actually fully comprehend. We like to have specs that are, well below 100 pages and that you actually can internalize and understand every single feature of the language and use appropriately. We don't want to have a PhD or worse, a faculty chair in C++, for instance. So Go is an attempt to sort of solve this problem. In the meantime, Go has been released to the open source in 2009. Just last week, actually, we celebrated the launch of Go 1. Go has become more than just a programming language. It has become a programming environment. And while we used to call it a systems programming language originally, we now are feeling, we've taken this a little bit more liberal, and we call it a general purpose programming language. So Go is compact. There is not that many language features. It's hard to give a good measure for that, but one measure might be the number of keywords, which is 25, which is very low. Yet it is expressive. We believe in providing orthogonal features that you can freely combine, as opposed to having a new feature for the new paradigm that's coming along, and then you sort of have to understand how this new feature interacts in very, very subtle ways with every other feature of the language. It's statically typed and garbage collected. It is object but not type oriented, and by that we mean you can employ an object-oriented style if you like, and there's very good reasons why you want to, but you're not, A, forced into that style, and B, you're not required to deal with a plethora of type system stuff that comes in there. There is very strong concurrency support. One of the key goals for Go was to provide support for the new future of hardware. It's very efficiently implemented. We have 2 native compilers. It has a powerful standard library, and in the meantime, a very much growing set of development tools, including a brand new build tool that, when you use it together with basically with just Go code, feels like you work with an interpreted language like Python. So it's very scripty feel to it. So just to start out with, the typical Hello World program, the typical Go program starts with a package clause, tells you which package this file belongs to. There is an import statement. There's function declarations. There's nothing particularly fancy here, and nothing unexpected. You can see strings have full Unicode support. This is something that's just standard and should be expected from any modern language these days. Now, there's more to Go than just the language, and there's a strong library, as I said before, and here is an example of Hello World 2.0, if you will. This is an HTTP server that implements Hello World, so when you go to this link below here, you will get a Hello World reply here. And this is all you need to do. You refer to the HTTP package, you start the server in your main function, and you implement this handler. And we'll get to this handler over the course of this talk a few times, so it's good to internalize the signature. There is a response writer where your response goes to, and there's a request where your request comes in. And at this point here, we don't care about the request, we just write something down. And so when you run this, Yeah, maybe I should connect first, I guess. Okay, let's do that. That is a very bizarre situation here. Yeah. So I'm connecting to my local host, but for some reason I have to go through. Yes. And 498 C3. Right, yeah. Okay. I should probably also start my server. Yeah. And here we go. We should be getting there, and that's good. Now I just need to say hello here. And voila. So you get your hello world. Okay, this is now running, and we'll be using this in the next examples. So how do we recognize Go code? If you look at Go code, you will see that there is declarations. They are very familiar. Look a little bit like cleaned up Pascal. There is import statements. There's const declarations, type declarations, variable declarations, and so forth. Why is this a left to right style as opposed to the typical C declaration style? Well, it makes a lot of sense. Type declarations actually become understandable. Everybody who has tried to declare the type of a function that takes a function argument and returns a function result in C or C++ knows what I mean. We have powerful strings. Strings are built-in basic type. We have composite literals, as you can see here, the last example, last var declaration. Declarations are usually of the form keyword, name of the object that you're declaring, the type, if there is any, and initial value, if there is any. Statements, on the other hand, use a cleaned up C style. Why? Because it makes a lot of sense. There's nothing wrong with them, but we definitely cleaned them up a little bit. So the curly braces are mandatory. It's good style. And once you do that, then you can get rid of all the extra parentheses. Also, you will notice that there is no semicolons. They're actually in the language, and you can write them. But there's a very, very simple and a syntactic rule when you can omit them. And it turns out you can omit them almost always. And we avoid some of the pitfalls that you have in other languages like JavaScript. So this elimination of the semicolons, or if you will, the introduction of semicolons happens at scan time and it's context-free, and so it's very simple. So how is Go different? So I'm going to talk about these three aspects: object orientation, the concurrency model, and handling of exceptional situations, because I think these are three parts that are implemented in Go in a different way than in other languages. So first of all, we have methods without classes. And this doesn't mean this is a prototype-based language or anything like that. It just means that we don't need to declare a class to give any type a method. We have interfaces without hierarchies. And we have a mechanism to get to code reuse without using inheritance or other mechanisms. Communication and concurrency is built into the language. It's not part of a part of a library that you have to import, and as such, the language comes with concurrency support built in, with batteries included. I mean, it's right there, out of the box, ready to use. Handling of exceptional situations is something that is traditionally done with try, catch, finally, and throw, and the typical kind of exception handling mechanisms that you find in other languages. In Go, we deferred the design of this aspect of the language for a little while, and we came up with a sort of minimal conclusion, if you will, but that has some rather interesting properties. So let's talk a little bit about methods and interfaces. So here you have a declaration of a point, which is just a struct, and there's nothing fancy here. This is just like a C struct, and Go structs are just C structs essentially. And so we want to have a function that prints this point, or returns a string for this point, a string representation. And the point-to-string function here is just a regular function that would do this as you could do this also in any other language. And when you call it, you have a static dispatch. Now, we want to convert this function into a method. And in Go, a method is simply a function with a receiver. And the way we accomplish this is by moving the first argument, in this case, the only argument, in front of the function name. And this declares this as a method. And by virtue of point being the type of this receiver, we know that this is a string function of the point type. Sorry, a string method of the point type. And so now you can call this string method using the dot notation. And you still have static dispatch. So this is, at this point, simply syntactic sugar. And it turns out that in much code of the world, this is actually all you need. And a lot of people, not in this crowd, of course, but a lot of people don't even know that this is not really what is the object-oriented part of the language. But as soon as you write it like this, it looks object-oriented. And it certainly has a lot of syntactic advantages because you can chain more easily. And you also get a namespace. The string method is now in the namespace of the type, so to speak. So in Go, methods can be attached to any type, including your own built-in, your own float type or your own byte type or whatever. So here we declare two types, Celsius and Fahrenheit. These two declarations, they introduce two different types and they're not assignment compatible. So this is very useful in a lot of situations. So you don't have to introduce like a unit mechanism, for instance, and so and by virtue of these two types being not compatible with each other, you cannot freely mix and match them without explicit conversions. And so we define again a couple of methods here: string on Celsius and Fahrenheit, and they do what you would expect. And there's a little conversion function at the bottom. And there needs to be an explicit conversion here. There's no assignment compatibility. That's generally true in Go. That was a somewhat difficult decision, but numeric types do not automatically convert to the greatest common, not the lowest common, not the GCD, the opposite. So they don't. So if you mix an int and the float, you don't get a float in as a result. You have to explicitly cast the integer value into a float and so forth. And the reason for that is the experience that some of the contributors in this team had over decades of programming in languages like C and C++, where these conversions happen automatically and lead to errors that are impossible to find, especially when you convert between, let's say, an int 16 and an int 32, or an int 16 and an int, which is different on different platforms in size. I think this is actually a very good decision. So how does this all come together with interfaces? So an interface is a type where you simply define a set of methods. There's nothing new here, nothing unusual, except that now any type that implements all the methods that are defined by a particular interface are automatically assignment compatible to variables of that interface. You do not have to say that my particular, Celsius or Fahrenheit type implements the stringer interface. It just does, because it implements the method string, and the stringer interface here only has one method, the method string, and therefore you can assign them. And this has proven to be an extremely powerful way of composing software. Naturally, all interfaces, all values implement the empty interface, because the empty interface here at the bottom has no methods, and any type has no methods, at least no methods, so you can assign it to a variable of the empty interface. This is sort of the equivalent of a void star, but it is actually dynamically type checked when you unpack these things again. In the system, there are a lot of common interfaces in our library, and the reader and the writer interface here are two typical examples. They're very pervasive, they're used very often and frequently, and a lot of library objects implement the reader and the writer interface, and as such they become plug and play compatible. So can go through this quickly. So here we have the dynamic dispatch. We have a value of the of type point, a value of type Celsius, and we have a variable of type stringer. Stringer is an interface. Now I can assign a value, the value corner to v, because corner is of type point, which implements the string method, and v is a stringer. And so when I then say v.string, I'll get the point printed out. Similarly, for the Celsius type. When I convert it, I'll get a Fahrenheit object, which again implements the method string, which I can therefore can assign this value to the stringer variable and so forth. I can actually should be able to show this running. Here's the Go playground. There's the same code that you've just seen before. It looks like it's properly formatted, yes, and so I can execute it, and you will get, what you would expect at the bottom. So I've mentioned before, interfaces are typically very small. There's maybe 1 to 3 methods, and some key interfaces are pervasive in the standard library. One of them, for instance, again, mention them, the writer and the reader interface, and one application here is the copy function in the I/O package. The copy function in the I/O package takes data from a reader and copies it by writing to a writer. And the reader and the writer, they can be anything. Typically a reader is a file. The writer could be a file, but it could be a network connection. It could be an encoding library. It could be an encryption library, anything like that. And interfaces are introduced ad hoc, often after the fact. That's another important aspect, because often when you deal with very large code bases where a lot of the code existed before you came on board, before you had a say in the design, or maybe the code has been bought and you don't have any control over it, you cannot change it, and you still need to interact with it. You cannot go and say, I want this piece of library object here to implement my interface that I designed after the fact. You just want it to implement your interface, and in Go you can just write that down. There's no explicit hierarchy. Hierarchies are hard to get right in the beginning. It might be possible when a project grows. Designing the correct object hierarchy is often turns out maybe not to be quite correct, and when your system and that you're writing is large enough, you may not have the bandwidth anymore to make those changes, and your system becomes odd.
So is it correct to say that when you assign to an interface, you box whatever you're assigning, and then
That is correct. I mean, maybe there's boxing, maybe not. If there's space, there is no boxing necessary. But essentially, an interface variable is a tuple. It's a type descriptor, if you will, and it contains something like analogous to a vtable and the value.
Is that multiprocessor safe?
Yes, because the construction of the vtable, if you will, happens at assignment time. And then when you actually do the dynamic dispatch, it's a vtable lookup. There's no inline caching going on, anything like that. So it should be fine. So here's an application of what we just seen. This is a different handler, a file handler, instead of the Hello World handler that we've seen. And in this case, what this is doing, it's reading some value, some form value that you may provide via an HTTP request, opening that file. If the file cannot be opened, then it prints an error and returns. But if it can be opened, then we just copy it to the response writer. And because a file implements a reader and the response writer implements a writer, I can just write this, and I'm done. And so if I actually go here, I get, I just looked at this piece of code here, server.go, and I'm getting like this code, shown in my web browser. Now, our HTTP library is quite powerful, and it does sniffing of the data that you're, writing back through the response writer. So in this case, I wrote a text file, and so I got the right content information, and my browser showed a text file. But I can also, do something completely different. I can see if maybe there's a picture of a gopher, and sure enough, I got an image server. And this is all that I wrote. I wrote like 5 or 6 lines of code, on top of this original Hello World example. So let's do something more interesting. A Mandelbrot server. So we wanna do something that does something like this, where I can zoom in, have different enlargement factors, and so forth. And so how would you do this in Go? Again, using this existing model here, how do we represent the Mandelbrot image? Well, it is a struct, and in our case, it has an origin. That's the left bottom corner. It has a pixel size in the complex plane. It has an image size and a number of iterations, things like that. And I'm going to implement 3 methods, namely these red methods here: color model, bounce, and the at method that gives me the color at a particular point. It turns out that these 3 methods implement the image.image interface. And the library provides a function that encodes an image.image as a PNG file. And so this is all I need to do to get this image on my web page. Yes, I have to implement iterate and color for, but these are small functions, maybe 10 lines of code or 20 lines of code. And so this is the actual implementation of the server. Here is my Mandel handler. Version 0. It has, again, a response writer and a request. Coming in, I declare a variable of type Mandel. I fill the values in that I got from the URL, and then I just do PNG encode. And the PNG encoder, again, takes an image and writes it to my response writer. That's all I need to do. And there you go. You got your Mandel 0. So quick digression. So in Go, functions are, of course, values to their first-class objects, their closures. I don't need to go into much detail here. Here's a little geninc generator. You provide an int value n, and it returns a function that does inc n. And these are true closures as you would expect. So we want to see how fast is our Mandelbrot, server, and so instead of writing a specific piece of code around my specific handler, I'm just going to write a handler generator that provides the corresponding logging that I'm interested in. So this is a little closure generator, if you will. It takes a handler func. This is the handler functions that we've seen before. It makes a logging handler func, and there's nothing fancy to it. So if I have this, I can run this again, and I can now see how much time it took. And so this is a native Go implementation. This is a 600 by 600 pixel image with, I think, let's say 1,000 iterations. And it took a little longer. So let's run this a few times. So that takes now 1.4 seconds. It's pretty speedy. So Go runs at the close to the speed of C++. It is a safe language. We have array bounds checks and we have garbage collection, and you have to take that into account. There's a little bit of overhead, but in principle, there's nothing that prevents us from running as fast as a true native language, if you will. So interfaces in practice have worked out really, really well. As I mentioned most of the points already. We introduce interfaces often ad hoc, just to plug and play to get pieces to work with each other. They're very lightweight. There is not much a priori design necessary that is often wrong over the course of a project. It's very easy to change. So the next different aspect of Go is Go routines and channels. Go has what we call the Go statement. And what the Go statement does, it takes as an argument, if you will, a function invocation and then launches this function as a coroutine, as a separate thread. And you can think of them as like coroutines. We call them coroutines naturally. The next piece of code shows you how you would launch n coroutines. That's all you do. Off you go. Coroutines are often closures. It makes a lot of sense because often you have a little piece of code that you want to write there and you don't want to write a special function somewhere and pass parameters. Coroutines are implemented through segmented stacks, so they have their own stack. The stack segments are allocated on the heap. The initial segment size is very small, maybe 4K, I believe. So the number of coroutines that you can launch is only bound by the amount of memory that you have. And it is no problem on a small laptop like this to launch 100,000 coroutines, start them up, connect them all through channels, send a token through all of them, shut them down in like a second. So coroutines are super lightweight. Now, channel is the means to communicate between coroutines. And at this point, it should become clear this is very reminiscent of Tony Hoare's CSP. This is directly a concrete implementation, if you will. A channel is essentially a FIFO queue that has synchronized push and pop operations. We call them send and receive. And you can make channels of buffer channels and unbuffered channels. If you have a buffer channel, let's say of n elements, then you can push or send up to n elements into this channel before your operation blocks. If you have an unbuffered channel, then you can only write to the channel if somebody else is on the other side and actually wants to receive that channel. So that you have a synchronization operation at that point. So a channel is created through a make construct. You tell it what type of channel it is. You tell it whether it's buffered or not. You can send to the channel and you can receive from the channel. Yes?
So coroutines can read and write memory also, right?
Yes.
So then they can communicate via shared memory?
Coroutines can communicate via shared memory, and we have libraries with the typical, synchronization primitives and mutexes and stuff like that. But the recommendation is don't do it. Once you do that, you are in, parallel concurrent code hell. You get all the complexity that you have. It turns out, of course, you get the same problems with channels and coroutines, but the same problems such as, you can get deadlock, you can get starvation, all these kind of things. But it turns out, in practice, it is much, much easier to program with channels and coroutines. So let me show you some examples. Here, as I said before, channels are the means to communicate with coroutines because they do the synchronization work for you without you having to deal with it. So here we create the channel C that accepts some kind of result type. And here we launch a coroutine as a closure. And in this closure, we do some work concurrently. And when we're done, we send the result to the channel C. And then later, we want this result. And so we receive from the channel C. So at the point X becomes the receiving of C, you block until you get that value. So this is a very typical coroutine, a Go concurrency pattern. There's no explicit synchronization. We use channels for communication, closures as the coroutine. And one of the mantras is mentioned here at the bottom. We do not synchronize to communicate. We communicate to synchronize. And it turns out that makes life a whole lot simpler. Yes?
What if the channel fails?
What do you mean by fail?
Well, what if the partner fails?
If
the Go phone fails.
Depends on how it fails. You mean if it never sends anything?
Yeah, it doesn't send anything.
Yes, then you wait forever. So this is a shared memory model. The data that you write into the channel is copied, but if you send a pointer, you copy the pointer, not the underlying data structure. This is a systems programming language. How do you deal with these kind of things? Well, one model that we're using in our code is if you do some work, let's say on some large data structure, a tree, and you're done with that work, then you send back maybe the root of that tree, and by that you're communicating to the receiver, you're not touching this anymore. There are some conventions. The language doesn't give you, absolute security here, but we also get, as a side effect, we get the speed. Let me show you a simple work queue scheduler, or work stealing scheduler here. That's all you need to write. This is a fully working work queue scheduler. N is, for instance, the number of actual cores you have on your system. So what do we do here? We create a queue, a buffered channel that takes as arguments closures, closures without arguments and that have no result, and then launches N of those coroutines that you see here. And each of those coroutines does nothing else but read from the queue, like wait for the next closure that's coming in, running it, and that's it. And so how is this? And then we return the queue here. Now this queue is returned, of course, asynchronously, because all all the closures here in the middle, they're spawned off. So I'm now creating such a queue by calling scheduler of 4. And I'm using another channel, the result channel that I use for my functions. And now I'm just like submitting all those closures into this queue. And in those closures, I do whatever work I want to do. When I'm done with that work, I send the result back through the result channel. And now this scheduler just takes all these closures and runs them, one at a time as they come in, but it spreads them over those N coroutines. And whoever gets done first sends the result back first, and so forth. So let's do a better Mandelbrot server using this mechanism. The approach is, let's do a sequential draw instead of what we did before, like an explicit drawing into an image, and then try to make this a parallel or concurrent version. So here we have our Mandel handler 1, the next version. Looks very similar, except that instead of calling P and G encode and just send in the actual Mandel object and then sort of query each pixel through the add interface, I'm actually drawing it explicitly. And so we look at draw 1 here. Draw 1 is just a method that actually explicitly creates an RGBA image in this case. There's nothing magic to it. There's the creation of the image. We loop over all lines. We loop over all the pixels. We set each pixel, and we use the add mechanism that we had before, and then we return the image. And it turns out that this runs actually a little bit faster than what we had before. So let's do this a couple of times. So this is Mandel 1, Mandel 0. Let's do this a couple of times, and then now we look at the logs. We see the 200 milliseconds are from Mandel 1, the 300 milliseconds are from Mandel 2. The 200 are from Mandel 1, and the 300 milliseconds are from Mandel 0. And they should actually run almost the same. But in this version here, the encoder knows a little bit more. It knows this is an RGBA image, and so it can do a little bit more. Before, it didn't know that. It just had like an abstract image object that it had to query for each pixel, and so it was a little bit slower. Now, let's convert this into a concurrent draw. Again, the simple most approach here is to draw this image explicitly, but we treat each line as an independent unit of work. And so because we do this, we need to return each line independently, and so we need to have a data structure here that represents a line. The Y tells us which line, and the data is the actual color data for that line. And then we use a coroutine to compute the pixel data for each line and the channel to send the computed line back. And so this is how the concurrent draw looks like. And again, so this is taking the old draw and making very, very small surgical changes, and the red code is the change. That's all you need to do. So here we launch a coroutine for each line. It takes as an argument the line Y, which we have to pass in because we want to actually make a copy. Note this is a real closure. If we wouldn't make a copy, we might get the Y of the next iteration, as this is a real closure, and we capture the outside variable. So we allocate the data. We range over the data. This is a sort of simplified for loop here for iteration over arrays. We compute the data, and then we send the line back. We send a pointer to the line back through the lines channel. And then on the Mandelbrot server side, what we do is we have a little loop where we read m.h, so the number of lines we have, lines back from this channel, and then draw these lines explicitly in our image, and then encode the image. This is almost the same code, very little change, but we have now a completely concurrent version, and the lines that that are being computed more quickly will return more quickly. And so if we run this now, this is Mandel 2. Let's do this a couple of times. And so this is now down to 169 milliseconds. Now you would expect, this is a 2-core machine, it should run twice as fast, but of course that's not true. We actually do more work. We actually have to copy this line, and we have to send it back, and so forth. But we see the speed up, and there's nothing unusual here. But you can see how easy it is to transform something from a sequential version into a concurrent version. So my time is running short, so I'm going to probably cut the third piece a little bit. But let's just summarize this here. It's very trivial in Go to launch multiple threads of control. And what's important here is you can do this, of course, in other languages too. You can have C++ libraries where you can do almost the same thing. There's some work going on where you can have channels and things like that in other languages. But it is crucial that the overhead on the page, the actual stuff that you write, is very small. You are not drowned out on the page by the technicalities that have nothing to do with your problem. You can actually see what you're writing, and you can actually think and reason about your program, as opposed to having two or three pages of boilerplate for something that has that should be very simple. So let me just fly through this. We have a couple of interesting concepts in mechanisms in Go to handle with exceptional situations, and one of them is the defer statement. The defer statement is a statement that lets you launch a function, invoke a function, but then suspend it in midair. So it's getting launched, and it stops just before you start executing the body. And then the body is executed when you leave the surrounding function. So this is like a finally, that's kind of function scoped as opposed to block scoped. And so you can do some interesting things. For instance, this example here defers 10 print statements, and then they're being executed at the end of your code. And so so this function f here will print start, end, and then 9, 8, 7, 6, 4, and so forth. And what is this good for? It's extremely useful to do things that have to do with cleanup, such as closing a file, but things that you only have to do under certain conditions. This is a statement, not a control structure. We use this in conjunction with what we call panics and essentially throws. If you have a panic, which is essentially the same as a throw in another language, then the deferred functions are still being executed even if you unwind your stack through a panic. And so in this case, in this particular example here, we have a recursive function that panics once n reaches 0, and then unwinds the stack. But each time the stack is being unwound, it still prints whatever n is. And so by combining this with another mechanism, the recover mechanism, which allows us to test whether there is a panic ongoing and recover the panic value, we basically get exception handling. So again, the time is running out. I'm not going to go into detail here. There's a lot of very good documentation on our website. Let me skip through this. There's much more to go. We have here's a few items. We have mathematically precise constants. We have very good support for composite literals, which allows you to build very, very large tables, for instance, that are being then memory mapped when you start your function, your application. We have a mechanism which we call embedding, instructs, which allows us to get some of the effects of inheritance and even mixins, if you will. We have type switch statement. We have a select statement for multiplexing over several channels. Support for variadic functions in the language, not in the library. Very strong program initialization support and others. So where are we at? We launched Go 1 last week. This is the culmination of more than 4 years of work. The main reason for this launch and release is stability. We plan to not change the language in the foreseeable future. We try to keep the library completely backward compatible. In the meantime, we have lots of startups, a lot of community out there that is using Go and wants to rely on Go for their future projects. Go is also on App Engine. It's supported on several Unix versions. So OS X, FreeBSD, several Linux versions for 32-bit, 64-bit, x86 architectures, as well as ARM. And yeah, I mentioned already App Engine. Thank you. So I encourage you to try it out.
Thanks. So if you unplug, we have time for a few more questions while we set up for Andre. So there's one here.
So do you think you can simulate using Go routines the semantics of the C# async await?
Probably. It would look a little bit different. It's probably more explicit. I tried, for instance, it's very easy, for instance, to implement a future using Go routines. It's like 6 or 7 lines of code, and you get the effect of what you would do with a future mechanism in another language. So,
what mechanism do you use to grow the stacks of the Go routines?
Whenever you invoke a function or a method, there's a little check in the beginning that checks whether you reach the boundary of your current stack segment, and if necessary, it is being expanded.
I was wondering why the Go routines need so much syntax. Why do they need to be built into the language? Is that?
Well, that's a long debate, but I believe it's very hard to provide really, really good concurrency support without language support. One of the statements I haven't showed here is the select statement, which allows you to multiplex between several channels, all of which may or may not be able to send or receive. And without doing this in the language, it's going to be very, very, very difficult to do in the library, I believe. Yeah.
3 quick questions. Do you have tail calls? Do you have a GC that runs on multiple cores at the same time? And can you wait on multiple channels at the same time?
There's no tail calls. Our GC is at this point a conservative GC, and it definitely could be improved. Yes, you can wait through a select statement. You can wait on many, many channels at the same time, and then proceed with the one that is ready.
So as you notice, it's really rewarding when you take an interest in Go. You get a gopher when you ask a question about Go. But I think we're ready to switch over now.